This is lecture 24 on matrices and linear maps, and just to be a lightning review of what's a matrix. And I think you guys already know, but just a quick review here. So if we have an m by n matrix, that means it has m rows and n columns. We say that aij is the ijth entry of A. My notation is Rm by n is the set of m by n matrices. Other people use like MAT of m comma n or something, I don't know, but you'll find different notations for the set of matrices in different places. This is just the notation I'm fond of. Anyway, so we can either write A as a bunch of columns glued together or as a bunch of rows stacked. I mean, there's other things you could do, I suppose, but those are the ones I usually think about. Two matrices of the same size are equal if and only if all the components match. That's to say A is equal to B if and only if Aij is equal to Bij for all ij. Of course, you can also judge equality of two matrices by all their columns matching or by all their rows matching. Given that that's how you define equality, it's natural then to define the sum or the scalar multiple of a matrix like so. And if you have two matrices which are multipliable, meaning that the number of columns in the left matches the number of rows in the right, so m by n times n by p, then AB is going to be an m by p matrix, all right, m by p matrix, and you can define it by this summation right here. The ijth component is the sum over k, aik, bkj, which of course you could look at as being the ith row of A dotted with the jth column of B. And this formula further simplifies in the case that A or B, if A is a row vector or if B is a column vector, then you don't have both indices here, but this formula still kind of makes sense. But anyway, we'll talk more about the matrix column multiplication in just a minute. So next up, linear transformation is a special kind of function. Linear transformation is a function such that you can pull constants out and you have this additive property. So collectively, I call this linearity. And some people would say the fundamental theorem of linear algebra is that given a linear transformation from Rn to Rm, given a function from Rn to Rm, it's a linear transformation if and only if there exists a matrix which gives its formula, all right? And so here's a quick sketch of the proof of that right here. If there exists an A, so I'm starting with the converse direction, I guess. If there exists an A m by n matrix such that L of x is equal to ax and c is a real number, x and y are vectors, then L of cx is a times cx plus y, but by properties of matrix vector multiplication, you pull out the constant and break up the sum, and then that's CL of x plus L of y. So that shows you that if there's a matrix formula for the function, then it's linear. And conversely, if L is linear, then I'll explain more next page. L of x is equal to the sum over xi ei, which you can pull the sum over xi out, and that gives you lei. And this is a linear combination of vectors lei with weights xi, and so that's the matrix L times x, where I'll define L next page. So basically, that's the main thing, is if you've got a matrix formula for the function, it's a linear transformation, and only if that's possible is it a linear transformation. So here's the some of the details on that. So standard basis, E1 through En. These are ones and zeros, 1 in the ith spot, 0 elsewhere. And so you can build any vector from a sum of the standard basis times the Cartesian components, if you will. And here, to find the ith Cartesian component, you can take x dot ei. We talk a lot about that in Calculus 3. With my students, usually, the dot product selects components. It's also true in Rn. And so this is that remark I was mentioning. So in the case of matrix times column vector, matrix times column vector can be understood as x1 times column 1 of A, x2 times column 2 of A, plus xn column n of A. In other words, the matrix column product is a linear combination of the columns of A with the weights given by the components of X. Some books take this to be the definition of matrix column multiplication. So with that in mind, when you look at the previous page here, we've got this sum weights xi, and these are vectors. So this is exactly the product of a matrix times x, and that matrix has like the first column is L of E1, the second column is L of E2, and so forth. And that is in fact how I've defined the standard matrix of a linear transformation. Bracket L is L of E1, L of E2, L of En. This defines the standard matrix of L. And here, the standard matrix of L is an element of R M by N. Notice that the order of the letters switches over here. M goes with the range, N goes with the domain as it happens. So returning to the forward direction of that theorem on the previous page, here's the details once more in view of the definition right above. If L is a linear transformation and x is expanded in terms of the standard basis, then L of x is what we can pull the sum over xi out, LEI, and then that is xi times the ith column of the standard matrix, which then is exactly the standard matrix times x. So there you go. Of course, these things may have not been really said in this way in your linear course, and that's fine because your instructor is probably after something else than I'm after. Anyway, all of that just to motivate why we care about the standard matrix, because it's a way of understanding linear transformations. So here's I've got 5 examples for you where I just calculate the standard matrix for a linear transformation. I hope these are helpful to you. Example 1 here, and notice my notation is a little bit sneaky. This is my notation for a column vector, like that. If I use the angled curly brackets, the parentheses here means I use that it's kind of a sneaky notation for column vector like that. And this one, L of E1 is 1, 3. L of E2, in other words, put x equal to 0, put y equal to 1. So x equal to 0, y equal to 1, that gives me a 2. X equal to 0, y equal to 1, that gives me a minus 4. So 2 minus 4 is L of E1. Likewise, put x equal to 1 and y equal to 0. 1, 3, 1, 3. And so you put them together, you got 1, 3, 2, minus 4 as the standard matrix of L. You okay? Yeah. Oh. So, and then, there is proof positive that it works. So if we take that matrix times xy, we get back the formula again. So it works. Example 2. Let's see here. Come on, paper. So L of xyz is 2x, 3y, 4z, which gives us 2, 0, 0, 0, 3, 0, 0, 0, 4 times xyz. So another way you can look at this is just to take it and write it as a matrix times a vector. Whatever matrix you get will be the standard matrix. A third example. Come on. Paper's sticking. Third example here. If I have L of xy is x plus 2y, 3x plus 4y, 5x plus 6y. So here, L is a mapping what? this L is going from R2 to output is R3. So we should expect that the standard matrix is 3 by 2. And in fact, it is 3 rows, 2 columns. 1, 2, 3, 4, 5, 6, just like that. And you can also look at it as x times the vector 1, 3, 5 plus y times the vector 2, 4, 6. That linear combination is this matrix product. So again, thinking of the matrix multiplication in that way may or may not have been emphasized by your instructor, and that's okay. But it's useful to know about. So this is example 4. Here I have L of xyz is x comma 2y plus z plus 3z. So this is a mapping from R3 to R3, so we expect the standard matrix is square. And here it is. 1, 0, 0, 0, 2, 1, 0, 0, 3. So I hope these help you. If you didn't know what a standard matrix is already, I hope these clear it up for you. Here L is a mapping from R3 to R, so that makes the standard matrix is going to be 1 by 3 in this case, 1 row, 3 columns. I put commas in when it's just a row vector. Okay, so that's pretty much it. That's all I got to say about this one. So next up, we will look at the Frechet derivative and how this, because the reason we're talking about this is because the whole point of the Frechet derivative is that we need replacing a function with an affine version of the function. It's essentially its linearization, and corresponding to those, we can look at the matrix of that linearization, and that's called the Jacobian matrix. So that's where we're going next. Thanks.